All right, let's come back to this. So um, the state function one, you don't have to worry too much about it. Um, most of the function that we're talking about is going to be state functions. And the definition of a state function is that it only depends on the initial state as well as the final state. So in this case, we have a picture like this. So the state function would be the height or the altitude. It only depends on the position A as well as the position B. It really doesn't matter whether you go around the mountains to get from A to B. The altitude difference from A to B is still the same. It doesn't really matter whether you go up to the top of the mountain, go to the B. As long as you get to the same initial and final state, the value is the same. In this case, the altitude is the same. It's called a state function because it's independent of the path that you take. In reverse, you also have things that are path function, which depends on the path. So in this case, the time that you take to get from A to B depends a lot on the path, right? You can go around and around and around of the mountain, or you can go directly from A to B. So the time that it takes from one place to the other, like when you're driving here, for example, is a path dependent. That's an example. So another example would be, I don't know why this thing is in black and white, but in terms of our thermodynamic, the problem that we have is that the amount of heat and the amount of work that we get from a particular process is also a path-dependent function. So for example, I have a ton of coal, right? So I have a ton of coal. If I put it in a locomotive like this, I can convert a lot of them into work. Whereas if I simply burn my coal just on an open air, what happens is that the amount of energy that I get, all of them is going to be converted to heat. I can still burn the same amount of coal, but depend on what processes that I apply to it, so what function, what path I take it to, I can either get heat or work. So far so good? Yeah. Basically, your car is also a path-dependent function. The gasoline in your car, the one that you consume, is, some car is more efficient than others, and some of them is not. So that's a path-dependent function as well. Now, that's kind of good and all. That's kind of annoying because what we want to know about chemistries, or actually in science in general, is not just to measure things. So if you've taken mechanical physics, you know the mass of this locomotive and it moves at this amount of speed, so you know the amount of energy that expended. For example, what is the amount of work that is being performed? But the thing about science is that we not only want to just be able to measure it, we want to be able to tabulate its value, want to make predictions out of it as well. Hence, the equations of enthalpy that you saw just now is created because if you look at the structure of enthalpy, enthalpy is also considered a state function. So let's go back to the example of the state function that we have. So this U is the internal energy. And as I mentioned before, as long as the gas is moving really, really fast, if you have another exactly the same gas molecule moving at the exact speed and so on, then the internal energy must be the same. Therefore, the internal energy is a state function. And if you look at the structure of enthalpy, H is U plus PV. U is a state function. It's just really how fast the gas is moving. And if you know the pressure and the volume of the gas, it really doesn't matter whether you pressurize the gas, increase the volume, pressurize again, so on. As long as the pressure and the volume of the gas is the same, then the state is the same as well. So P and V are both state function. State. This is state. This is also a state function. Right? So H is a state function in that regard. And later on, we're going to look at the change in the Gibbs free energy as well as entropy. They're all state functions. Now, how do we get things that are considered path function, like work and heat, to force it to turn into a state function? Well, simply what we have to do is we have to restrict the condition. Right? You can't just do a work. If you want to make the value of heat that you measure to be a state function, you have to restrict the conditions of the amount of heat or the amount of work that you perform. So in this case, So what among the restriction that you do, if you perform heat and you perform some experiments and you measure the amount of heat exchange, as long as you do this process at a constant volume, then the amount of the heat you measure is going to be equal to the change in the internal energy. So this is by restriction, right? So we restricted that this is only true when the volume that the work that we do or the process that we do is constant. Then whatever heat exchange that we measure is going to be equal to delta U. And the same with the process at a constant pressure. As long as we perform our work or whatever process we do at a constant pressure, then the amount of heat exchange must be equal to delta H. And now this becomes a state function. We must restrict the condition to make it into a state function. And once we have a state function, it's kind of nice and easy because it becomes, we can start having to use these values that we collected to make some prediction from one to the other. Right? Now, an example for that is just a chemical reaction. So I have a chemical reaction going from A to B. It really doesn't matter whether we're looking at delta U or delta H and so on, as they're all just state function. So I know that if I do a chemical reaction, I know the bond between the molecule changes, but as long as I start from the same place and ends at the same place, the amount of energy that I will produce in the end must be a state function as well. So I can, for example, turn A from A to, say, D, and then from D to B. It really doesn't matter what path I take. I still know that from A to B, the amount of energy released is the same. Because the chemical bond structure between one molecule to the other is the same before and after. Therefore, there must be the same level of changes from one molecule to the other when I do this chemical reaction. Now, that's why when we're doing a chemical reactions, if you look at the back of your book, a lot of the chemical reactions are tabulated at a constant pressure. Again, because whenever we're doing that chemical reactions, we can measure the amount of heat produced, and as long as we do the reaction at a constant pressure, then the value that we get, so if we burn some material, say a bunch of coal at a constant pressure, whatever heat that we get from that particular burning of the coal is going to be equal to the delta H. So it becomes a state function. So what happens is that if I want to know, if my goal is trying to figure out how to get from A to B, what is the amount of energy that I will get from A to B, I can do, say, from A to D. And if I know from D to B, then I should be able to calculate the amount of energy that I get from A to B. It really is just like using a ruler. The picture looks more complicated, but it's basically a ruler. If I know from, if I want to know from A to B, I don't know how much that takes the energy, but I do know from A to D, it takes me 6, and I know from B to D, it takes me 4. So therefore, from A to B must be 6 plus 4, which is just equals to 10. So I can start making prediction based on incomplete information. As long as I know before and after, I know the path from one to the other, then I should know the amount of energy that I will get from a chemical reaction. This whole thing is just a prediction. And this really is what you will learn closer to majority of the class. And if anybody taken high school chemistry, yeah, so that's basically Hess's law. The whole equation that you've done when you're doing chemical reaction in Hess's law are done at a constant pressure in order to be able to predict some other random reaction. Yeah, sorry. If we burn coal at a constant pressure, then the amount of heat that is being released is going to be equal to the change of enthalpy. Yeah. At a constant pressure. It's Thermodynamic is kind of tricky because whenever we're talking about energy, we have to classify it as work, heat, internal energy, enthalpy, Gibbs free energy, and so on. So the energy itself you kind of have to classify it in one way or the other. And again, restrict the condition if you're trying to figure out from one to the other. Okay, that's kind of mostly what we're going to get through for this class. It's just using the amount of energy that is released from a particular chemical reaction. You can measure it, and then from that measurement, figure out some kind of state function dependent. But before we go there, we're going to go back to heating and cooling again. And essentially, suppose that I have 2 or 3 or 5 objects together. So suppose that I have hot water. Suppose that I have a hot piece of metal and I put it in some kind of cold water. That I know some heat must be exchanged from the hot to the cold, so until the temperature is equilibrating. And as long as I assume that there's no heat escaping to the atmosphere, then the conservation of energy is going to be conserved. That is, the sum of the energy that is being exchanged, so sum of heat exchange, must be equal to 0, because you neither create nor destroy energy, so it's just a statement of conservation of energy. And similar to our exercise last time, if the process occurs at a constant pressure, Q is just going to be equal to NCP delta T. Before we were using NCV delta T, but in this case, since we're going to be mostly looking at processes at a constant pressure, the equation that I'm going to change is that I'm just going to change that CV into CP. So there's going to be a bit more practice on how to do this as well, and it's going to be very similar, and mostly it's going to be algebraic practice. So the one that I want you to do for now is just do exercise 1. So what is the change in temperature? Exercise 2, I'm going to put 40 grams of copper that's hot into 40 grams of water that's colder. What is the final temperature? Now, before you start doing this exercise, the point is pretty straightforward. In order to measure the amount of energy released in a chemical reaction, we use what they call the Bohm calorimeter, which I'm going to explain later. But essentially what you do is you put the material that you're trying to react inside a really rigid container, and you do chemical reactions inside of it, and usually things get really hot. So this is going to be hot, right? And then the hot object is going to transfer its heat to the surrounding water. And if you know the amount of heat that you transfer between one object to the other, this is the Q from that you release is really equals to the delta H, or the energy that is released from the chemical reaction. So in order to understand this, we kind of need to know how does heat exchange work with simple objects like 2 pieces of metals or just water and something else. But that's kind of the reason that we're trying to study it. We want to be able to master the calculations in order to then be able to measure the amount of energy released in a chemical reaction. So let's just do exercise number 1, and then do exercise number 2. Number 1 is pretty straightforward. Number 2, the idea is also straightforward. You have a piece of copper. Because of 40. The algebra is annoying, but the 2 equation that you want to use for number 2 is, whenever you have heating and cooling, is mCp delta T. And then conservation of energy, we simply put these 2 things together. So Q1 plus Q2 equals to 0. And in this particular question, number 2, you're trying to solve what is the final temperature if you put these two objects together.